This is Paris Podcast number 75, and today we're continuing the podcast series. Last podcast 74, we looked at the first part of flapping wings in ground effect, corrugated flapping wings, by the way. This is the second part. So if you haven't listened to the first part of the corrugated flapping wings in ground effect, go listen to podcast number 74, then come back to this one. So to look into this phenomenon, we're going to look at a paper called Numerical Investigation on the Aerodynamic Efficiency of Bio-Inspired Corrugated and Cambered Airfoils in Ground Effect. And this is open access, so you can find it in the link in the description. In the last podcast, we're going through some of the previous findings from other researchers about how corrugated wings and wings in general that flap are affected by the ground effect. And we went through a bunch of different theory and findings, so they were quite cool. So let's continue on now with this current study, which involves numerical analysis and some experimental results. So let's talk about how they set up their numerical. Hold on, let me just get the stop timer again. Remember last time I'd had 20 minutes, it wasn't that successful, but I'll try again. So after 20 minutes, I'll try to stop the podcast. I'll just go too long and then start the next podcast. So that way they're in 20-minute blocks instead of continually getting bigger and bigger as they seem to be doing. So this is hopefully going to work. Anyway, the numerical setup they had, they say that typical turbulence models in this approach are K epsilon or K omega models in their different forms. So K epsilon was really one of the first turbulence models to have come about. It came about primarily in the 90s in terms of it being very popular, but it's sort of obsolete now. Like there are much better ones that we use all the time, and they're going to discuss this. So flow fields predicted by K epsilon models are generally inaccurate under adverse pressure gradients and boundary layer separations. So pretty much for almost everything, because everything has some sort of boundary layer separation at some point, and adverse pressure gradients usually, like there are very few applications where you won't get these things happening, at least one of these things. And so these models are not therefore recommended for applications to pitching airfoils, of both of these are critical. Now, why do we use these turbulence models? Well, if you were to use something called DNS, you wouldn't need to worry about it, or even LES. But because we're using something called URANS or RANS or DES, which means that we are simplifying the models to the point where we're not actually resolving turbulence in the boundary layer, we are approximating it. We're using some sort of stochastic approach. So we're saying, okay, we don't really know what the turbulence is, but we're going to say it's approximately this. And we're using these equations. And this is where K epsilon or K omega or anything else that you're using come into play. They're very important, and the accuracy of your solution really depends heavily on these models that you use. As we're mentioning, K epsilon and K omega are not great. K epsilon particularly. K omega is pretty decent. However, they say the downs, and they use it to remedy the downside of the K epsilon not performing well in adverse pressure gradients and boundary layer separations. However, the drawback of the K omega model, which is the kind of improved version, I guess you would say to some extent, the drawback of the standard K omega model is that the solution is too sensitive to free stream values of K and omega, which are the turbulence and the dissipation rate outside the shear layer. So this breaks down in other parts of the flow. So again, you don't get as accurate a simulation. Now, generally speaking, for airfoils, K omega is far better than K epsilon, particularly in transitional regimes. However, they're both not that great. K epsilon is okay if you're going to be going up to like very high Reynolds numbers, like millions of Reynolds number. But even then, K omega is better. So to overcome this, they're using the K omega SST model, which is designed to avoid such free stream oversensitivity and avoid the problems with adverse pressure gradients and boundary layer separations. And I've touched upon the SST K omega turbulence model quite a few times in other podcasts. I'm a massive fan of this, primarily because it is so robust and it really helped me out a lot in many different situations, particularly with laminar separation bubbles when you're trying to simulate them. But even with something as unintuitive, or I shouldn't say unintuitive, a lot of people think it's unintuitive, cars. So I remember talking with quite a few researchers how they often say, oh, K epsilon is great for cars and bluff bodies because they're bluff, so it's very turbulent. But in reality, it's still not very good. In the SST K omega turbulence model actually performs much better, and it will solve a lot of problems, even in this situation. So my go-to turbulence model is K omega SST, or SST K omega, whichever one you want to say it. And for that reason, that it is just so robust and very reliable. So getting back to what they're simulating here. So remember in the last podcast, we talked about a dragonfly wing inspiring this research, because dragonfly wings have like this corrugated wing. And remember how we said that where you are on the wing, the corrugation will be different. So if you're at the wing root or the wing tip, and you like cut the wing, the corrugation will be different. And along with if you're at the leading edge or trailing edge, there's going to be different crinkles in it, so different crinkle cuts. And they have a picture here which has a dragonfly wing and 3 cross sections. And depending on where you are in the wing, these cross sections are different. And this can be for a bunch of reasons. One would be for like strength, so torsion and rigidity, because depending on where you are in the wing, it's going to be having different loads on it based on the different vortices that are around it producing or being used to produce lift. So that different corrugation will help with the strength, but also the different corrugation will help with the aerodynamics. So they're going to produce different vortices or take advantage of the vortices in different ways, or even prevent laminar separation bubbles in different ways, etc. And as you go from the wing root to the wing tip, the wing's translational velocity, so it moving up and down or back and forth, will be different. So different corrugations do make sense. So let's move on to their computational domain for their CFD. So reason why I want to talk about this is how they set it up. So they have their wing, which is next to a wall. They move this between one chord from the wall, so one wing like length, one wing from the wing leading edge to the trailing edge, that length from the wall, up to 5 of these distances away. And it's 12 of these distances from the inlet and 20 from the outlet. So it's decent. It's not ridiculously good, but it's okay. And it's about 12 times that distance from the other side of the domain. Now, the reason I want to talk about this is that this domain is effectively a rectangular prism, so cubic kind of idea. And the reason why this is important is because it's not a typical way that you would set up a domain for a stationary wing. But the reason why it's different is because this is actually a flapping wing. So how does this change this setup compared to a stationary wing? Well, with a stationary wing, everything is the same except the inlet. So the inlet, instead of it being square, you would have like a semicircle. So it'd be like curved at the front. And the reason why we do this is because when we want to simulate the wing at different angles of attack, we put the velocity at different angles. We don't move the wing usually because that will change the domain, the meshing and etc. We often just change the velocity. So instead of it being straight on in the X direction, we have it in the XY direction a little bit. That way we can change angle of attack without actually changing the mesh setup. So that's different. Whereas with this flapping model, because the velocity is always just going to be in one line and it's in the same direction, but it's the wing that's flapping, the wing is producing the change in angle of attack itself. So, and because we're using an immersed boundary method here, which we covered in the last podcast, it makes sense to be able to do this as well. So that's why this setup is different to a traditional setup that we do use for wings usually, or for airfoils usually. So let's talk about the boundary conditions a little bit more in the geometry. So the corrugated and NACA 4412 airfoils were selected to be investigated in the ground effect based on the aerodynamic coefficients in the flapping motion. So the corrugated airfoil implemented in the present study corresponds to the cross-section of the dragonfly forewing along the dragonfly's wingspan. Kessel, a researcher, extracted 3 cross-sections as I mentioned earlier. They're all different, and that was illustrated in figure 1A. These sections were labeled profiles numbers 1, 2, and 3, 2 being the middle one. So the geometry of the dragonfly's wing profile varies depending on where you are in the span. Profile number 2 was chosen for this study. So let me just quickly describe what profile number 2 might look like. So if you're listening to this, which you can actually watch the video on YouTube or on Spotify, but if you're listening to this, I'll quickly describe it too. So profile 2 has at the leading edge is very crinkled, then it sort of dies out. So it's a bit flatter as you get towards the trailing edge. Profile 1 doesn't really have that. It's just really crinkled all over. And profile 3 doesn't have as much crinkle to it. It's a bit more gentle in how it forms. So those are really the differences. Profile 2 is probably the most unusual in terms of the leading edge has a lot of crinkles, the trailing edge doesn't. So that's a quick description for you. So the wall has a no-slip boundary condition, which means that a boundary layer will form over it. And based on the inlet flow velocity and airfoil chord, the Reynolds number was 50,000. So that's right in the region where you're going to get an LSB forming, but because it's a dragonfly wing, it won't have one. And if you don't know what I'm talking about, podcast number 74, I go through that, which is really cool. Okay, so looking at the mesh, the reason I want to talk about the mesh is because they have similar meshes between the dragonfly wing, the crinkled wing, and the NACA 4412, except at the leading edge, the mesh is far finer for the corrugated wing, I should say. I'm still thinking about potato chips, crinkle cuts, but it's corrugated, I should say. Whereas for the NACA 4412, in front of the leading edge, the mesh is much coarser. I don't know why that is. If you have an idea, let me know. But I was trying to figure this out. I thought it might be due to the boundary layer mesh, but it doesn't make sense for that to happen. I would imagine that the 4412, if that were the case, would actually have a much finer mesh near the leading edge than the corrugated wing because of the boundary layer mesh, but that's not the case. So I'm not sure why that is. All I know is that the corrugated wing has a much finer mesh well upstream compared to the NACA 4412. So does that make a difference? Well, to look into that, they looked into something called a grid and time step independent study. So the grid independent study is where you change the mesh and you see how this affects the results. The time step independent study means you change the time step and you see that affects the results as well. The idea of this is to get to the point where it doesn't change anymore with increasing fineness in either one of these two parameters. So they looked into 3 different setups, coarse, medium, and fine, they call it. And the number of cells range from 55,000 to 250,000 or so. Now, a typical way that you would look at the grid independent study is that you can change the number of points you have in each direction by whatever you have times the square root of the cube root of 3. The cube root of 2. Why we do the cube root of 2 is because you have 3 directions, and the cube root of 2 times cube root of 2 times cube root of 2 equals 2. So by changing each one of these directions by a cube root of 2, the overall grid is actually now twice the number of cells as what you'd have in the original grid. So you're just increasing the number of cells by a factor of 2 each time. And this is a typical way that we'll just go about it. The way that they've done it here is they not only change the number of cells, they've also changed the number of boundary layers for the inflation layer, or however you like to call it in whatever CFD or software you're using. They also changed the first layer height. Now, these are all good things to look into, but changing them all at the same time makes it hard for the researcher to figure out which one of these parameters was actually causing the differences. Now, if you don't really care about that, you just want to get an independent solution, go your hardest, it's fine. But if you want to understand why changing these parameters do affect their solution, this is a fairly fairly difficult way to determine that because there's no design of experiments behind it, etc. They also changed the growth rate of the boundary layer mesh as well. So that's, again, another parameter. So, but they found that with, they say the difference in the drag coefficient between the medium and fine grids, which is between 120,000 cells and 250,000 cells, is less than 2%. Therefore, in this study, they used the medium grids for the NACA 4412 and Dragonfly airfoils. So let's look at the time step now. This is important because we're using URANs, remember. So URANs means that we're taking account the time component of the flow, whereas RANs by itself doesn't take account of the time. So the grid and time step sensitivity analysis is performed at pitch amplitudes of 10 degrees, true numbers of 0.4, and Reynolds numbers of 50,000. So why is this important? So the Struhl number is just a way of understanding how quickly the wing is flapping. And the time steps range from 0.001 seconds to 0.01 seconds. So a factor of 10 difference. They say, according to figure 6, it can be seen that the drag coefficient between the time steps of 0.005 seconds and 0.001 seconds are very close, which is due to the slight difference in about 1%. So the time step of 0.005 is chosen for the rest of this paper because that saves calculation times, which is all true. So now let's look at how these different grids affected the NACA 4412 airfoil drag coefficient when it was flapping. Now, interestingly, for the 2 finer grid setups for NACA 4412, they mimic each other very closely, like along with time, they're almost bang on each other all the time. the very coarse grid, so the coarsest grid that they looked into, the 55,000 cell one, interestingly, the drag coefficient plot looks like a sine wave with time. But the first peak, the drag coefficient of this very coarse cell is, this very coarse grid is significantly higher than the other two grids. But then for the second peak, it's significantly lower. So there's a massive non-uniformity to it, and it seems like it's just not very accurate in terms of, but not very repeatable to begin with, and not accurate as such. So the very coarse grid sucks, which is often the case. And similarly, for the Dragonfly-inspired drag coefficient, a similar sort of thing happens where the coarse grid doesn't really mimic the other two very well. However, it is significantly better than the NACA 4412 in that it is periodic and repeatable. So that's good, but it's still not great, whereas the other two grids, finenesses, they are much better. So then they looked at the drag coefficient variations versus time for the different grids for the NACA, this is NACA 4412 FL now. And with the different time steps, the coarsest time step is pretty terrible. It's completely off in terms of phase and even in magnitudes. Whereas the other two time steps, 0.005 seconds and 0.01 seconds, match each other very closely. So that's quite nice. Now, they say, in order to validate the solving method in this study, the results are compared with wind tunnel measurements and other URANS numerical test cases from another study. It is a NACA 0012 airfoil and moves with a pitching motion at a pitching amplitude of 6 degrees, frequency of 0.188, which is how quick it's flapping, incidence angle of 12 degrees, and a Reynolds number of 100,000. So figure 7 shows a comparison of aerodynamic coefficients with the references. So let's look at figure 7. Now, interestingly, the experimental work is they're using as sort of the gold standard. For the drag coefficient, there's very little hysteresis, which means that when you increase angle of attack and you decrease it, the drag coefficient is pretty much the same at each angle of attack. So this is one thing that happens often in airfoils where if you have funky flow physics, when you increase angle of attack, you might get one drag coefficient or one lift coefficient, but as you reduce angle of attack, then you get a different drag coefficient, different lift coefficient. That's because the flow physics that's formed is different. So when you're going up, the flow physics is being carried through from the low angle of attack. When you're going back the other way, the flow physics is coming from the high angle of attack. And one major flow physics change is the separation. So when you increase angle of attack, the separation point, the flow isn't separated. So you get a continuous lift generation. But once you go to a high angle of attack and the flow separates, you have to then get the flow to reattach before you produce lift again. But that means you have to drop the angle of attack significantly for that to happen. So that's why we get hysteresis. So they say the projected peak value of the drag coefficient of the present work differs by 5% compared to the experimental results. While the other reference, the numerical reference that they're comparing to, differed by 22%. Due to using the transitional SST model that we mentioned earlier, current CFD outcomes project a secondary leading edge vortex that assists the recovery of lift and drag coefficients about the maximum angle of attack. Therefore, the accuracy of the present study is higher than in the numerical reference and is closer to the experimental results. So in other words, this is much better because the SST gamma K-Omega approach. Now they have a really cool figure that shows the drag coefficient of the Dragonfly airfoil at different heights above the ground over one oscillation. So this is really cool because they have the drag coefficient with angle of attack. And interestingly, the ground effect doesn't really come into play until you get very close to the ground. So they have heights from 1 chord from the ground to 5 chords to the ground. But it's not until you get to 2 chords to the ground that the drag coefficient changes dramatically. So between 2 chords to the ground and 5 chords to the ground, so that distance away, all the drag coefficients mimic each other quite closely. But once you get to one chord from the ground, the drag coefficient dramatically changes. In fact, you're actually producing a lot more thrust at high angles of attack because of this flapping motion. So they cover this. They say the effect of the mean distance from the ground. The airfoil's mean distance from the ground is varied from 1 chord to 5 chords. In figure 9, the time history of the drag coefficient for Dragonfly airfoil is shown at various distances from the ground. As the ground level approaches, hysteresis loop becomes wider and the value of thrust, so negative drag, produced increases. As illustrated in figure 10, when the height from the ground is changed from 5 chords to 2 chords, the values of the average lift coefficient over one oscillation period increase by approximately 1.1%, so almost nothing, bugger all. But increasing it to, but reducing the height from the wing to the ground to 1 chord, the average lift coefficient dramatically increases. They say when that happens, the average lift coefficient goes from 0.085 to 0.095, so 11.7% increase. That's how sensitive the ground effect is to the height of the object above the ground in terms of flapping wing. So they also have the drag coefficient of the NACA 4412 compared to the drag coefficient of the Dragonet fly airfoil. Now, I'm going to leave it here because my timer just went. I'll just finish this little bit. So for the NACA 4412 airfoil, comparing that to the Dragonfly airfoil, the NACA 4412 airfoil has a significantly better drag coefficient. So it's lower, which means that you're producing more thrust. It's also more negative on average compared to the Dragonfly airfoil. So in podcast number 74, I was mentioning how typically airfoils found in nature are much better than what we produce because Mother Nature has evolved them to be better in what they're doing. This particular finding might suggest that actually the NACA 4412 is better than what Dragonfly wings are like. But the lift coefficient of the Dragonfly airfoil, the average one, is significantly better than the NACA 4412. And the reason why that is, so let me get this graph up. Figure 10 shows the lift coefficient of the Dragonfly airfoil at different heights above the ground. So you can see it ranges from minus 0.8 to plus 1. So it's a 1.8 range. If I were to compare this to the NACA 4412, the minimum is minus 0.4, the maximum is 1.2, so the range is 1.6. So that means the NACA 4412 doesn't have nearly as great a range of lift production as the Dragonfly airfoil. So even though it is better in terms of drag, arguably, lift production is not as good. And this is why the Dragonfly airfoil is better. The corrugated airfoil is better when we're in ground effect and flapping. So that's what I wanted to cover in this. So we can't just look at the drag coefficient, we have to look at the lift coefficient and overall the performance of the airfoil to get an appreciation of how good an airfoil is. And this shows it. So that's in this podcast. I'll see you in the next podcast. We'll wrap up this study. And if you do experiments, or if you do CFD actually first, check out the courses we do to make you better at CFD. You can learn from beginner stage all the way to advanced. Check out the Atmosphere Hawk, which is an experimental instrument that we make, which accurately measures the density of air. If you don't know how the density of air changes your results from day to day, check out podcast number 54, where we go through how on every experiment, regardless of whether you're a very expert experimentalist or not, the density of air changes and that changes your results. And that makes validating CFD harder because the density of air that you're using in a CFD is different to your experiments. So you're not comparing apples with apples, you're comparing apples with oranges. The Atmosphere Hawk is the instrument we make to get rid of that error and make your CFD easier to validate and make your experiments more accurate. Get one for yourself, link in the description. Peace out, amigos.